why Voyager 1 will still be out there, long after the sun is gone. 5 billion years from now, the sun will die. It will swell into a red giant so enormous that it swallows Mercury, then Venus, and then, in all likelihood, the Earth itself. Every mountain, every ocean, every city, every trace that our species ever existed will be erased in fire. But roughly 2 light years away, drifting silently through the cold and the dark, one small machine will still be out there. It was built in the 1970s with less memory than the key fob in your pocket. It runs on technology from the era of disco and 8-track tapes, and it will outlive the sun itself. This is the story of Voyager 1, the most enduring object humanity has ever made, and why it may one day be the only proof that we were ever here. Before we go any further, if you love stories about how far human curiosity can reach, hit subscribe. Every week on this channel, we explore the search for life and the strange, distant worlds waiting beyond our own. You do not want to miss what is coming next. Now, on the surface, this claim sounds absurd. How can a machine assembled by human hands in 1977, a machine older than the personal computer, outlast a star that has burned for 4.5 billion years? Our intuition tells us that everything breaks down. Cars rust, buildings crumble, phones die after a few years. Nothing we build lasts even 1,000 years without constant repair, let alone billions. But here is the thing our intuition gets wrong. Almost everything that destroys objects on Earth simply does not exist in interstellar space. There is no oxygen out there, so nothing can rust or corrode. There is no water, no wind, no rain, no weather of any kind. There are no bacteria to decompose anything, no plants to grow through cracks, no earthquakes, no fires. The two great destroyers of everything humans build, chemistry and life, are completely absent. Once you leave the solar system, the universe becomes an almost perfect preservation chamber. The only real threats left are radiation slowly darkening surfaces over millions of years, and dust grains, tiny micrometeorites that sand away at a spacecraft one atom at a time. And in the nearly empty void between the stars, physicists have calculated that erosion at that rate would take longer than the current age of the universe to seriously damage Voyager's structure. The spacecraft does not need to fight for survival out there, it just needs to keep drifting. And drifting, as it turns out, is the one thing this spacecraft does better than anything else. To understand how it got there, you need to go back to the summer of 1965, to a graduate student named Gary Flandreau working a part-time job at NASA's Jet Propulsion Laboratory. Flandreau was given an unglamorous assignment, mapping out where the outer planets would be in the coming decades. And as he plotted the orbits of Jupiter, Saturn, Uranus, and Neptune, he noticed something that made him stop cold. In the late 1970s, all 4 giant planets would line up on the same side of the Sun in a sweeping arc. It was an alignment so rare, it happens only once every 176 years. A spacecraft launched at exactly the right moment could use the gravity of each planet as a slingshot, stealing a little momentum from each one, and visit all 4 worlds in a single mission. Miss the window, and humanity would have to wait until the middle of the 22nd century for another chance. NASA called it the Grand Tour, and in the political and budgetary chaos of the early 1970s, the full plan was nearly canceled entirely. The agency salvaged it by building 2 nearly identical spacecraft, Voyager 1 and Voyager 2, officially approved only to visit Jupiter and Saturn. The engineers, however, quietly designed them to survive far longer than the mission on paper required. They knew exactly what they were building. They just could not say it out loud. Voyager 1 launched from Cape Canaveral on September 5, 1977, 16 days after its twin. And the machine that left Earth that day is, by modern standards, almost comically primitive. Its 3 onboard computers have a combined memory of about 69 kilobytes. A single photo taken on a modern smartphone would not even come close to fitting in it. Its data recorder is an 8-track tape machine, the same basic technology people used to play music in their cars in the 70s. It transmits with about 23 watts of power, and by the time that signal crosses the Gulf to Earth, it arrives at a strength of less than a billionth of a watt. Detecting it requires antennas the size of buildings, and a level of patience that borders on devotion. And yet this primitive machine was built with a kind of engineering paranoia that modern devices rarely receive. Nearly every critical system has a backup. Some have backups for the backups. The thrusters that keep its antenna pointed at Earth were designed to fire hundreds of thousands of times. They have now fired millions. When the primary thrusters degraded in 2017, engineers switched to a backup set that had been sitting unused since 1980. 37 years of silence. Then a command crossed 13 billion miles of space, and the dormant thrusters fired perfectly on the first try. The power source is the real key to its longevity. Voyager 1 does not use solar panels because sunlight in deep space is far too weak. Instead, it carries 3 radioisotope thermoelectric generators containing plutonium-238. As the plutonium decays, it produces heat, and that heat is converted directly into electricity. No moving parts, no combustion, nothing to jam or wear out. Just the slow, steady physics of radioactive decay, losing about 4 watts of output every single year, as dependable as time itself. Keeping a conversation going with this machine is its own quiet miracle. On Earth, the task falls to the Deep Space Network, a trio of giant antenna complexes in California, Spain, and Australia, spaced around the globe so that at least one is always facing the spacecraft as the planet turns. The dishes stretch up to 70 meters across, and even they strain to hear Voyager's whisper. The signal that reaches them is 20 billion times weaker than the power needed to run a digital watch. To pull real data out of that faint hum, receivers are chilled to just a few degrees above absolute zero, quieting the electronic noise of their own circuits, so the ghost of a voice from interstellar space can rise above it. Every bit of science Voyager 1 has ever returned. Every image of Jupiter, every measurement from beyond the heliopause, arrived through this needle-threading exercise, repeated daily for nearly 50 years. But before we talk about how it all ends, you need to see what Voyager 1 actually did on its way out. Because its journey through the solar system rewrote the textbooks in a matter of months. In March of 1979, it swept past Jupiter and returned images that stunned the scientists watching them arrive. It discovered that Jupiter has a faint ring system nobody knew existed. It captured the Great Red Spot as a churning storm larger than the entire Earth. And then came the moment many planetary scientists still call the single most important discovery of the entire program. A navigation engineer named Linda Morabito was examining an image of Jupiter's moon Io when she noticed a strange umbrella-shaped cloud rising off its edge. It was a volcanic plume erupting hundreds of kilometers into space. Io was not a dead ball of rock. It was the most volcanically active world in the entire solar system. Its interior kneaded and melted by Jupiter's immense gravity. This was the first time active volcanism had ever been seen anywhere beyond Earth, and it quietly transformed the search for life. Because if gravity alone could heat the inside of a distant moon, then worlds far from the sun could still have warmth, energy, and possibly liquid water. Every mission we have ever sent to hunt for oceans inside Europa or Enceladus traces its lineage back to that one grainy photograph. In a single afternoon, the habitable zone stopped being a narrow band around a star and became something that could hide anywhere gravity squeezes a world hard enough. The number of places where life might exist in our solar system multiplied overnight, and it has never stopped growing since. One overlooked smudge on one image, spotted by one careful engineer, quietly redrew the map of where we look for life. A year and a half later, Voyager 1 reached Saturn and pulled off its second act. It threaded past the rings, revealed them to be thousands of intricate braided strands, and then made a deliberate sacrifice. Mission planners steered it close to Titan, Saturn's giant orange moon, a world wrapped in a thick nitrogen atmosphere, the only moon in the solar system that has one. The flyby confirmed that Titan's chemistry resembles a frozen version of the early Earth, a natural laboratory for the ingredients of life. But that trajectory came at a price. Bending the flight path toward Titan flung Voyager 1 up and out of the plane of the planets, ending its planetary mission forever. There would be no Uranus, no Neptune, no more worlds. From that moment on, its destination was nothing less than the stars. And on its way out, it gave us one last gift. On February 14, 1990, at the request of the astronomer Carl Sagan, engineers commanded Voyager 1 to turn its camera around and photograph the Earth from 6 billion kilometers away. In that image, our entire planet occupies less than a single pixel, a pale blue dot suspended in a beam of scattered sunlight. Sagan later wrote that everyone you have ever loved, every human being who has ever lived out their lives on that tiny point of light. It remains, to this day, the most distant portrait of home ever taken. Minutes after the sequence finished, the cameras were shut down permanently to save power. Voyager 1 has been flying blind ever since. It does not need eyes for where it is going. For the next 2 decades, the spacecraft cruised through the outermost reaches of the sun's influence, a vast bubble of solar wind called the heliosphere. In 1998, it quietly overtook the older Pioneer 10 probe to become the most distant human-made object in existence, a title it will never surrender. In December of 2004, its instruments registered the termination shock, the invisible wall where the solar wind slams into the thin gas between the stars and abruptly slows down, like water piling up around a boulder in a stream. The spacecraft had entered the turbulent outer boundary zone of the sun's empire. Scientists knew that somewhere beyond it, the bubble had to end completely. Beyond it lies true interstellar space, the medium between the stars, filled with particles blasted out by ancient supernova explosions. Nobody knew exactly where the boundary was. And then, on August 25, 2012, the instruments aboard Voyager 1 recorded something extraordinary. The count of solar particles collapsed almost to zero. The count of galactic cosmic rays surged. The spacecraft had crossed the heliopause, the edge of the sun's domain. For the first time in history, an object made by human beings was sailing through the space between the stars. When a solar shockwave later rippled past the spacecraft and made the surrounding plasma vibrate, scientists converted those vibrations into audio. What they heard was a thin, rising tone, the sound of interstellar space itself. Several members of the team have described hearing it for the first time as one of the most moving moments of their careers. It is worth pausing to appreciate what kind of place the spacecraft now calls home. The space between the stars is emptier than the best vacuum ever created in any laboratory on Earth. A single cubic centimeter of it, a volume about the size of a sugar cube, contains on average just a handful of atoms. Temperatures hover near absolute zero, except where the ancient breath of exploded stars drifts as warm, thin plasma. There is no up, no down, no horizon, no day, no night. The sun behind Voyager 1 has already faded to nothing more than an unusually bright star among thousands. And this profound emptiness is precisely the point. It is the emptiness that will preserve the spacecraft, the way the dry silence of an Egyptian tomb preserved artifacts for thousands of years. Except this tomb has no ceiling, no walls, and no end. But surviving out there and staying in touch are two very different problems. And in November of 2023, the mission faced the closest brush with death in its entire history. Voyager 1 suddenly stopped sending science data. In its place came an endless, meaningless repeating pattern, the spacecraft equivalent of a flat line. For 5 months, engineers at JPL worked the problem, and the odds looked terrible. Every command they sent took 22.5 hours to arrive, and any reply took another 22.5 hours to come back. A single question and answer consumed nearly 2 full days. The original designers of the computer systems had long since retired, and some had passed away. The team dug through binders of engineering documents written before some of them were born. Eventually, they traced the failure to a single, corrupted chip in the flight data system. They could not repair it, so they did something remarkable instead. They rewrote the spacecraft's software, chopped the affected code into pieces, and tucked those pieces into unused corners of a 46-year-old computer's memory, transmitting the patch across 15 billion miles. In April of 2024, Voyager 1 resumed speaking clearly. The room at JPL erupted, engineers hugging over a machine launched when Jimmy Carter was president. The oldest spacecraft in history had been resurrected by people who refused to let it go. That resurrection, however, only bought time. The plutonium keeps decaying and the power keeps falling. Engineers have been switching off systems one by one for years, shutting down heaters, sacrificing instruments, squeezing out every last watt. Sometime in the next few years, most likely before the early 2030s, there will not be enough power left to run a single science instrument. Not long after that, the transmitter itself will fall silent. There will be no explosion, no dramatic final message. One day the signal will simply fail to arrive, and the mission that has run for half a century will be over. Even then, we will not entirely lose track of it. The laws of orbital mechanics are so precise that astronomers can calculate where Voyager 1 will be for thousands of years into the future, down to remarkable accuracy. Long after it stops speaking, we will still know exactly where to point and say, there it is, still going. Children not yet born will learn its position the way earlier generations learned the names of constellations. In a strange way, the silent spacecraft may become more famous than the talking one ever was. A fixed idea in the human imagination, the machine that left and never came back. But here is what makes Voyager 1 different from everything else we have ever built. For every other machine, the end of the mission is the end of the story. For Voyager, it is barely the beginning, because nothing out there can stop it. The spacecraft is traveling at about 61,000 kilometers per hour relative to the Sun, faster than the Sun's gravity can ever reel it back in. It has, in the language of physics, escaped forever. Dead or alive, it will keep moving. In about 300 years, it will reach the inner edge of the Oort cloud, the vast shell of icy debris surrounding our solar system, and it will take roughly 30,000 years just to pass through it. In about 40,000 years, it will drift within 1.5 light years of a small red star called Gliese 445. By then, every word of every language spoken on Earth today will be gone, but the spacecraft will look almost exactly as it does right now, preserved by the vacuum like an insect in amber. And now run the clock forward. In 5 billion years, the Sun exhausts the hydrogen in its core and begins to die. It bloats into a red giant hundreds of times its current size, incinerating the inner planets. Then it sheds its outer layers into space and collapses into a white dwarf, a dense, dim ember about the size of the Earth, slowly cooling for eternity. Everything we ever were, gone. But by that point, Voyager 1 will be tens of thousands of light years away, orbiting the center of the Milky Way on its own path, an independent wanderer among the stars, no longer bound to the Sun in any way. The death of its birthplace will not even register. From that point on, Voyager 1 becomes a citizen of the galaxy itself, circling the Milky Way's core once every 225 million years or so, the same slow lap our Sun has been running since before the dinosaurs, and the galaxy it orbits will change around it. In roughly 4.5 billion years, the Milky Way is expected to collide and merge with the neighboring Andromeda galaxy, two islands of hundreds of billions of stars sweeping through each other in a gravitational dance lasting eons. Yet even that cataclysm poses almost no danger to the spacecraft, because galaxies are mostly empty space. Stars will be flung onto wild new orbits, but actual collisions will be vanishingly rare. Voyager will simply ride the currents of the merger like a leaf on a river, unharmed and unnoticed. Physicists who have modeled the long-term fate of the Voyagers estimate that erosion from interstellar dust and cosmic rays works so slowly that the spacecraft could remain recognizable for trillions of years. Some calculations suggest portions of it could persist in some form until the era when the stars themselves begin to burn out. In a very real sense, we have built something that operates on the same timescale as the galaxy, which brings us to the reason this story belongs to the search for life. Because bolted to the side of Voyager 1 is a golden phonograph record, and it may become the most important object our species has ever produced. In 1977, Carl Sagan led a small team given just 6 weeks to decide how to represent all of humanity to an unknown listener. They chose 115 images, greetings in 55 languages, the sounds of surf, wind, thunder, birdsong, a human heartbeat, and a mother's first words to her newborn child. They included 90 minutes of music, from Bach and Beethoven to Chuck Berry, from Senegalese percussion to a Peruvian wedding song. They even included the recorded brainwaves of a young woman, Andrian, who had just fallen in love with Sagan himself, and who spent part of the recording thinking about what it feels like to love someone. The record's cover is engraved with instructions for playing it, written in the universal language of physics, and a map showing the location of our sun among the pulsars of the galaxy. Electroplated onto it is a sample of uranium-238, a radioactive clock any advanced civilization could read to determine how long the spacecraft has been traveling. The record was built to remain playable for at least 1 billion years. Its grooves are cut into copper plated with gold, sealed inside an aluminum cover, and mounted on the side of the spacecraft facing away from the direction of travel, shielded from the slow sandblasting of interstellar dust. A stylus and cartridge are bolted beside it, so the finder does not even need to invent a way to play it. There were arguments over every choice. The team debated whether to include images of war and disease and decided against it, not to hide our flaws, but because a first introduction should lead with hope. They fought to include a Beatles song and were blocked by copyright lawyers, an irony Sagan found genuinely funny, that humanity's message to eternity was edited by intellectual property law. What survived those 6 frantic weeks is a portrait of a species at its best. It is a message in a bottle thrown into an ocean the size of forever. Will anyone ever find it? The honest answer is that the odds are almost impossibly small. Space is so empty that Voyager 1 will probably never pass within a light year of another star. It will almost certainly never be intercepted, never be played, never be heard. But the record was never really only for aliens. Sagan understood that from the beginning. It was for us. It forced humanity, for the first time, to sit down and answer a single question. If you could say one thing to the universe, what would it be? Our answer was not a list of weapons or borders or conquests. It was music, laughter, greetings of peace, and the sound of a heartbeat quickened by love. That is what we chose. And whether or not anyone is out there to receive it, that choice is now permanent. It will outlast the pyramids, outlast the continents, outlast the sun. There is one more thought worth sitting with. Right now, telescopes like James Webb are scanning distant worlds for the faint chemical fingerprints of life, and scientists estimate our galaxy holds billions of potentially habitable planets. We do not yet know if anyone is out there, but if some other civilization ever asks the same question about us, long after our star has died, the answer will be drifting quietly through the dark. A small machine, 5 billion years from now, still carrying Chuck Berry, still carrying a heartbeat, still carrying the fading memory of a pale blue dot that no longer exists. Humanity may not be eternal, but because of one spacecraft launched in 1977, the evidence of us just might be. If this story moved you the way it moves me, share it with someone who still looks up at the night sky. And make sure you are subscribed, because next time we are exploring the ocean hidden inside Europa, a world where scientists believe alien life could be swimming right now, closer to us than most people would ever dare to imagine.